Yes, welcome to the session under coordination compounds. I have already taken 3 classes and have explained some of the aspects of coordination compounds, including structural isomerism. The first part of isomerism, structural isomerism. Now I would like to continue with stereoisomerism, and then I would like to jump over to one of the theories to explain the coordination compounds, namely valence bond theory. Okay, right. So in the previous class I explained some of I explained the IUPAC names of some compounds, and I added some more compounds to this list. Some more IUPAC names with the formula. Then I explained what is EAN, and then isomerism, under that structural isomerism, and then stereoisomerism. I have explained structural isomerism, under that linkage isomerism, ionization isomerism, solvate isomerism or hydrate isomerism, and coordinate isomerism. I have explained these 4 under structural. Now today in this session I would like to explain the stereoisomerism. So stereoisomerism with examples, then valence bond theory. If you go back to your organic, the first part, haloalkanes, where you studied the optical isomerism and in your first year pre-university under head carbons you studied geometrical isomerism. So stereo means space. So compounds having the same molecular formula, but distribution of groups or atoms around the central atom in space is different. It's called stereoisomerism. As I said, stereo is space or in 3 dimension. This comes under what is known as configurational isomerism, not conformational, configurational isomerism. Before I go to the coordination compounds exhibiting this, I would like to explain. So under stereoisomerism we have got, just like organic, we have 2 here, geometrical isomerism and optical isomerism. Under stereoisomerism we have geometrical isomerism and optical isomerism. Going back to first PUC, geometrical isomerism. Suppose you have a compound of this type, an alkene of this type, CAB, AB. C is connected to 2 different groups. Due to the restriction in the rotation of the double bond because of the twisted pi bond, the lateral overlapping of the p electrons or orbital, it cannot be twisted, it cannot be turned, it cannot be rotated. Therefore, this compound cannot be converted into this compound just by rotation. restriction in the rotation. Here A and A, the similar groups are on the same side of the double bond. This is called a cis compound. Here A and A are across the double bond. This is called the trans compound. So geometrical isomerism is also called cis and trans. A, B, A and B. Should it be of this type, AB, AB? Need not be. See, even if you have, there should be restriction in the rotation on the double bond. A, B, A, C. This also exhibits geometrical isomerism. AB and CA. This is cis compound and other is called the trans compound. So if this is C A B double bond C A, this is trans, this is cis. If all the four groups are different, C A B C and D, we can explain, not C, we shall have E. We can explain this not with a common name cis and trans, but according to IUPAC system, it is denoted as E and Z system. Antigen and Zusammen. Zusammen is similar to cis and antigen is similar to trans. That system is entirely different, which I don't want to go into the details here. So anyway, we shall see geometrical isomerism in the case of coordination compounds. Consider coordination compounds having square planar structure. For example, PT NH3 twice Cl2, that is diamine dichlorido platinum. Diamine dichlorido platinum 2. So this ion exists as square planar structure. PT will be at the center, NH3 and NH3, Cl and Cl will occupy an imaginary square, the corners of the imaginary square, the plane. Suppose this is the plane, platinum will be at the center, Cl and Cl, NH3 and NH3. This is of the type M A2 B2, M A2 B2. You can arrange this as in one or the first, or you can arrange this in this fashion. Two structures are possible. M is the metal, A and B are the ligands. So it should be 2 plus, sorry, it should be 2 plus. This MA2B2 type exhibit geometrical isomerism. A and A are on the same side, B and B are on the same side. Therefore, the first one is the cis compound. Here, the similar groups are across the metal. B and B are across the metal. Therefore, this is trans. The meaning of trans itself is across. Trans-oceanic travels. That means it flies across the ocean. Transatlantic, across Atlantic Ocean. Trans-Pacific, across Pacific Ocean. So cis is similar groups are on the same side. Trans, similar group or across. So this is, so for this compound PT NH3Cl2, let us say NH3 is A, Cl2 is B, then you can arrange like this. This is trans and this is cis. The first one is cis, the second one is trans. This is also called cis trans isomerism. This cannot be converted into this by rotation because of the square planar structure, just like the restriction in the rotation on the double bond. Okay, suppose similar to the organic compounds, double bond A, B, A, C, A, B, A, B, C, M, A2, B, C. A and A are on the same side, therefore this is cis. If you exchange this C and A, if it goes there and if it comes here, then it becomes trans. So Ma2BC will also exhibit geometrical isomerism. Now example for this is again PT. Just I will look into the actual structure, if it is possible for me to give the actual structure of this. Okay, fine. So this should be, okay, PT NH3 twice Cl NO2, NH3 twice is A, Cl is B and this is C. It can have two structures like this, M, A, B and C, square planar, and this square planar with coordinate bonds with the central metal ion. This will exhibit geometrical isomerism. So A are on the same side, this is cis, A and A are across, this is trans. So here if you apply this platinum will be at the center, NH3 and NH3 on the same side, Cl and NO2 like this, to plus, so it will be cis. If it is to be trans, then platinum NH3, NO2 and Cl. See here, NH3 and NH3 are across, this is trans. So I have given you Ma2B2 type exhibiting cis trans isomerism, Ma2BC exhibiting cis trans isomerism or geometrical isomerism, then A, B, C, D all are different groups. This also exhibits geometrical. Three structures are possible for this. You may write by using the groups and the particular metal. So it will be like this. So here are the following: NH3 amine is A, NH2OH is B, NO2 is C, Peridine is D. A, B, C, D. This exhibits geometrical isomerism. Three structures are possible. This must be explained as cis and trans according to the IUPAC names. If you write this, note down the atomic number of nitrogen, atomic number of oxygen, atomic number of carbon. If they are on the same side, higher atomic number groups are on the same side, it is cis. If it is across, it is trans. So, going back, Ma2B2 cis trans isomerism, Ma2BC cis trans isomerism, MABCD cis trans isomerism. Even the bridged binuclear complexes of the type Ma2B4 will also exhibit geometrical isomerism. See here, Cl and Cl are on the same side. C2H5 thrice, that is triphenylphosphine are on the same side. Therefore, this is the cis compound. Cl and Cl are across and triphenylphosphine across. Therefore, this must be a trans compound. So, bridged binuclear complexes like Ma2B4. Here, A is C6H5 thrice P. B is Cl, 4Cl are there. This will exhibit cis trans isomerism or geometrical isomerism. So, this is about tetrahedral complexes or square planar complexes. Coming to the octahedral complexes, where the coordination number is 6. The central metal atom or ion exhibits the coordination number of 6. Here we can have the types A4B2, A and B are ligands. I would like to specify here, I would like to repeat that A and B are ligands. Ma4B2, Ma2B4, Ma4BC or Ma3B3, all of them exhibit geometrical isomerism. One of them is here, CO NH3 4 times Cl2 plus and Cl minus. CO NH3 4 times Cl2. So, you can arrange like this. This is the square. Cl and Cl are on the same side. This is called the cis. If Cl and Cl, one is above, another is below, the rest will be the same. 4 NH3 groups. See here, NH3, NH3, NH3 and NH3. This coordinate bond, coordinate bond, coordinate bond, coordinate bond, this will be plus. Cl and Cl are across the metal. This is the transform. So, in the octahedral complexes, if you have of the type Ma4B2, Ma2B4, Ma4BC or Ma3B3, you can have the geometrical isomerism. The geometrical isomerism is due to the restriction in the rotation in that particular plane. Next, suppose you have so this is the compound. You consider CONH3 thrice Cl3, that is triamine trichlorido cobalt 3. This is the compound. You can arrange like this. The two structures can be arranged like this. The octahedral one. See, in the octahedral, metal will be at the center. 4 ligands will be at the corners in the same plane. 1 ligand will be above the plane, 1 ligand will be below the plane. See, in the first structure, 1 Cl minus is above the plane, 1 NH3 is below the plane. Similarly, here also. In the first structure, Cl minus, Cl minus A. Cl, the chlorido ligand, is on the same side. Identical ligands lie on the same side of the metal. This is a special type of isomerism called facial meridional isomerism. If the same groups are on the same side, then it is called the facial structure. If they are not on that side, see here, Cl in between NH3, Cl, NH3, NH3, Cl. This is called meridional structure. So, for the compounds of this type, you can have facial and meridional structures. This comes under geometrical isomerism, a special type, the facial and meridional, having 3 groups, identical groups. RH, Cl3, Py3. Py is pyridyl. Okay. The next, COEN twice Cl2, Cl plus. En is ethane 1,2-diamine. The name of this compound is dichlorido bis ethane 1,2-diamine cobalt 3 chloride. It can exhibit cis trans isomerism. So it can exhibit cis trans isomerism. Then the octahedral complexes like Ma2B2C2 can exhibit geometrical isomerism. This particular compound can have 5 different structures. I have given example, I have written just 2, PT NH3 twice Py2 Cl2 Cl plus and minus, because so platinum, so here it should be like this. One of the structures is like this. I have written just 2. You can write 3, 4 and 5 structures for this. 5 are possible and you can assign the isomerism, geometrical isomers, cis and trans for them. Okay. After explaining geometrical isomerism, we can come to the next one of the stereoisomerism, optical isomerism. Compounds having the same groups but distribution of groups around the central metal atom is different, metal atom or ion is different, such that they will have different effects on plane of polarization or plane polarized light. Plane of polarization. Different effects on plane of polarization. One, you know that organic compounds in which if the carbon atom carries 4 different groups A, B, E, D, it will not have the point of symmetry, line of symmetry or the plane of symmetry. This is called the asymmetric carbon atom or chiral carbon atom or chiral center. Such compounds are always dissymmetric. Organic compounds which are dissymmetric exhibit optical isomerism. The two optical isomers are D and L. D is one which turns the plane of polarization in the clockwise direction, and L is one which turns the plane of polarization in the anti-clockwise direction, and this can be obtained only by experiment. This can be known only by experiment. But for D and L, we can write different structures. D and L are always like the object and the mirror image, which cannot be superimposed. Object and the mirror image which cannot be superimposed. Okay, you consider a complex of this type: platinum with 2 pyridyl ligands, 2 amine ligands and 2 chlorido ligands. You can arrange like this the first structure and the second structure. You find that in the first structure, Cl and Cl are on the same side. Here also Cl and Cl are on the same side. Therefore, this is a cis compound that exhibits geometrical isomerism. At the same time, the first structure and the second structure are like the object and the mirror image which cannot be superimposed. I told you just now, D and L are like the object and the mirror image which cannot be superimposed. One will turn the plane of polarization in the clockwise direction, another will turn the plane of polarization in the anti-clockwise direction. This, when the experiment is done, it shows that it is D and this is L. That means this compound exhibits both geometrical isomerism and optical isomerism. Both are cis forms, but one turns the plane of polarization in the clockwise direction, another turns the plane of polarization in the anti-clockwise direction. Therefore, this is called cis D and this is called cis L. What's the name of this? Let's not worry about, because you already know the names, the IUPAC names. Just for the heck of it, I am telling you. So this compound is diamine, dichlorido, dipyridyl, platinum 4 ion. This is -2, that is this, therefore it should be 4. Next, this is En. En is ethane 1,2-diamine. 1,2-diamine. This is the object and this is the mirror image. CO. So this will be plus and this will be plus. CO is usually oxidation state of +3. En is 0, therefore it must be plus. So This is like the object and this is the mirror image, but both are cis. Cl and Cl are on the same side. Cl and Cl are on the same side. Object and mirror image, therefore it exhibits geometrical isomerism as well as the object and the mirror image, optical isomerism. There is no symmetry in the molecule. The next one, CO En thrice 3 plus. CO En thrice 3 plus. This is tris ethane 1,2-diamine cobalt 3 ion. Here no geometrical isomerism. This is the object, this is the mirror image. These two cannot be superimposed on each other because it's in 3 dimension. Hence the object and the mirror image, if one is D, another is L. One which turns the plane of polarization in the clockwise direction, another in the anti-clockwise direction. So this is about optical isomerism. I have given you some examples for optical isomerism. I have explained what is optical. Now we shall pass on to the theories that have been put forward to explain the formation of complexes or coordination compound. One well-established theory is valence bond theory, or popularly known as VBT, valence bond theory. This was put forward by famous chemistry scientist Linus Pauling, a double Nobel laureate. He got first Nobel Prize for chemistry, and then after 11 years he got another Nobel Prize for peace. Linus Pauling has been considered as one of the doyens of chemistry of the 20th century. He made revolutions with his theory. He has written a book, Nature of Chemical Bonds. Probably this was first published in 1950s. Even after 70 years, almost 70 years, this seems to be an authority on the nature of chemical bonds. Okay, so VBT was put forward by Pauling. Now we shall see, or we shall apply valence bond theory to some of the complexes and try to explain the magnetic behavior also. It is found that sodium chloride will give one electron to form Na plus and Cl minus, such that it will have, both will have the octet structure. So one of the theories that explains is, if a compound, if an element or if an ion or any species has got 8 electrons in the outermost orbit, then it becomes stable. In the case of complexes, FeCN6 4 minus, FeCN6 4 minus, Fe has to become stable. It cannot form ionic bond, not possible, because it has to lose about 6 plus 2, 8 electrons. That means it has to become Fe8 plus, not possible. Or it has to get 12 electrons, 12 minus, that is also not possible. Ionic bond is ruled out. Then covalent bond, so many electrons are to be shared equally, that is also not possible. But the central metal ion should become stable. If it has to become stable, it should attain the electronic configuration of the next noble gas. Therefore, the central metal should accept electrons from the ligand to form coordinate bond. Therefore, they are called coordinate compounds. So, metals accept electrons and ligands give electrons. Therefore, ligands are Lewis bases while metals are Lewis acids. Lewis acids. When they accept electrons, the orbitals of the metals will overlap with the electrons given by the ligand to form hybridized or mixed orbitals. This is the crux of the valence bond theory. I will explain it with an example. NiCO 4 times nickel tetracarbonyl. Nickel atomic number 28. It is at 28 electrons because its oxidation state is 0. So it will have argon, then 3d8 4s2, 3d8 4s2. So I will write it 3d8 1 2 3 4 5 1 2 3 4 5 6 7 8 and then 4s2, then 4p 0. When carbon monoxide, the ligand atom, I am going to give you 8 electrons or 4 pairs of electrons. I need 4 vacant orbitals. Not only 4 vacant orbitals, but 4 vacant orbitals of equal energy. When carbon monoxide or carbonyl ligand approaches nickel, the 2 unpaired electrons get paired up against Hund's rule of maximum multiplicity. Against Hund's rule of maximum multiplicity, the electrons get paired. When the electron gets paired, one orbital is vacant. This is of lower energy. Therefore, the electron will be shifted from 4s. It will be shifted over here. This is better explained in the case under the theory, new theory, that is crystal field theory. Okay, after that you are left with 4 vacant orbitals, but of different energies. Now all electrons must be accommodated in 4 equal energy orbitals. Therefore, S and P3 will combine to form sp3 hybridized orbital. The 8 electrons given by there is no difference in the electrons which are already present and the electrons given by the ligands. Just to show it has been given by ligand, this is sp3 hybridized orbital and nickel tetracarbonyl exhibits sp3 hybridization, and here there are no unpaired electrons. N is equal to 0. You know that mu is equal to root of n into n plus 2. This will be equal to 0. therefore this is diamagnetic. Nickel tetracarbonyl sp3 hybridization, tetrahedral structure. So this is nickel, CO, CO, CO and CO. The bond angle is 109 degrees 28 minutes and it is diamagnetic because there are no unpaired electrons. Okay, so I will explain with a few more the valence bond theory. NiCl4, NiCl4 2 minus. Again, nickel atomic number is 28. Therefore, argon, I have left that argon. So it should be 3d8 and 4s2. But here nickel is present in +2 state. Therefore, it must be 3d8 and 4s 0. Of course, 4p is also 0. So like 3d8. One, 2, 3, 4, 5, 6, 7, 8. 8 electrons are there. 2 are unpaired electrons. Next one is S, another is P. But the thing is, when Cl, that is chlorido ion, approaches nickel, the lone pair of electrons are given to nickel, but chlorido is a weak ligand. It cannot force the electrons, the 7th electron and the 8th electron, to pair up. It cannot go against the Hund's rule of maximum multiplicity. Therefore, pairing will not take place, but chloride, 4 chlorido ligands are giving 8 electrons. This can be accommodated in sp3 hybridized orbital. sp3, 2 electrons here, 2 electrons here, 2 electrons is here and 2 electrons. Again, it is tetrahedral. It cannot make these electrons to pair up. Therefore, you have got n is equal to 2 and it is paramagnetic. It is even though it is sp3, just like nickel tetracarbonyl, sp3, this is diamagnetic, this is paramagnetic. Then take up NiCN 4 times 2 minus. NiCN 4 times 2 minus. So here nickel is 2 plus. Again 3d8, 4s 0, 4p 0. So 3d8, 1, 2, 3, 4, 5, 6, 7, 8. Even though time is over, I would like to explain one or two more coordination compounds according to valence bond theory. So 3d8, 4s and 4p. This nickel tetracyanido nickelate ion is diamagnetic, means n is equal to unpaired electron is equal to 0. Cyanido ion is a strong ligand. Therefore, it makes this 7 and 8 electrons to pair up. So you get 1, 2, 3, 4, 5. 2 electrons, 2 electrons, 2 electrons and 2 electrons. One vacant D along with one S. So 1 D, 1 S and P3. There are 5 vacant orbitals, but there are only 8 electrons given by 4 cyanidoligands. Therefore, 1 D, 1 S and 2 P will combine to form the hybridized orbital of the nature dsp2. The 8 electrons given by cyanide ligands are accommodated here. dsp2. How do you know it formed dsp2 and not sp3? If it had formed sp3 hybridization, there could have been 2 unpaired electrons, but here no unpaired electron. It is diamagnetic. It clearly shows that cyanide is a strong ligand. It makes the electrons to undergo pairing, forming one vacant orbital at d level. dsp2 is obtained and the structure is square planar. The structure is square planar. 4 times SO4. It is 2 plus and 2 minus. This is also form square planar structure. NH3, 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 NH3. Coordinate bonds with copper, and this will be 2 plus. This is the plane, the imaginary plane of the square planar structure. Similar to this NiCN4 2 minus also forms square planar structure dsp2 hybridization. So in this way we can explain the shape, to a little extent the magnetic behavior also. I will take up one octahedral complex CO NH3 6 times Cl3 or CO NH3 6 times 3 plus. Cobalt atomic number is 27. Here cobalt is present as 3 plus, therefore it must be 24. This one is 3d7 and 4s2, therefore it must be 3d6 and 4s0. So I will write 3d6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 and 6, then 4s, 4p. When NH3, 6 ligands are there, very strong, ammonia is a strong ligand. When all of them approach CO, amine, the ligand amine, hexamine cobalt 3 chloride, the amine ligand demands cobalt to form 6 vacant orbitals of equal energy. Not only equal energy, but it should be lowest energy possible. Ammonia is a strong ligand. To accommodate the 12 electrons given by 6 amine ligands, these 4 electrons get paired up. 1, 2, 3, 4, 5, 6. Therefore, you have 2 vacant orbitals on D2, and S is vacant, P is also vacant. Now 1, 2, 3, 4, 5, 6 vacant orbitals are there, but of different energies. Amine says, give me 6 orbitals of equal energy because all my 12 electrons are identical with each other. To accommodate this, then 3d6, so 6 electrons will remain here. D2 sp3, 1, 2, 3, 4, 5. D2 sp3 hybridization. It forms D2 sp3 hybridization where the 12 electrons given by 6 amine ligands are accommodated. I have told you the dotted line just shows there is no difference in the electrons of D of the metal and that of the ligand. Just to show that it is being given by ligand, I am writing like this. The 12, 1, 2, 3, 4, 5, 6, 12 electrons are given by, donated by 6 ammonia ligands, because each ammonia ligand will give a lone pair. So 6 are there, so it will form an octahedral complex. How do you know that it forms D2sp3 hybridization or not others? When D2sp3 hybridization is formed, all electrons are paired electrons, it is diamagnetic. All are paired electrons. N is equal to 0, mu is equal to 0. Therefore, it explains satisfactorily the formation of D2sp3 hybridization, and the structure of this is octahedral. It is octahedral structure. CO, NH3, 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 NH3 and NH3. All these will form coordinate bonds. They are going to give electrons, and I have told you why it accepts the electrons, to satisfy that EAN rule. Cobalt, and this will be 3 plus. So 4 will be in the same plane as the metal, 1 amine above, 1 amine ligand below. This is octahedral complex and it is diamagnetic. Okay, so I have explained some, a few, 3 or 4. One is CO, octahedral complex, CONH3 6 times, 3 plus. Then NiCN4 2 minus, NiCl4 2 minus with a weak ligand, NiCO4 CO with a strong ligand. I have explained today the valence bond theory, formation of sp3 hybridization, dsp2 hybridization and 1 d2sp3 hybridization with tetrahedral structure. This is square planar structure and this is octahedral structure, tetrahedral. Okay, the rest, a few more, I will explain in the next class. So with this I have explained the valence bond theory of some of them. So today I have explained stereoisomerism, geometrical and optical isomerism, and valence bond theory of a few complexes. Okay, I will continue with it in the next class, some more coordination compounds with a valence bond and then crystal field theory. Thank you very much. Now get access to the class practice packs sent by me, and with a passport you work out those problems or questions. Thank you very much.